Hello guys, I'm Paul McWhorter and I am here with Arduino lesson number 18. Hopefully you've tuned in for the last 17 lessons. These lessons tend to build on themselves, or if you come in with some experience on Arduino, you can just jump right into this lesson. What we're going to do here is we are going to use the virtuabotix ultrasonic sensor combined with the Arduino and a servo to make a little gizmo that will measure distance. And if you look here, we've got a quick kind of overview of it. We have the Arduino microcontroller. It is connected to the virtuabotix ultrasonic sensor that is making readings, and then you display to the user the reading with a servo with a little arrow hooked up to it. You can see that we've got it running live down here, and what we have is the ultrasonic sensor is here. We've got a little ruler so you can kind of see what the distances are, and then I have a little target of purple sticky notes. And so what you can see is that the distance from the ultrasonic sensor to the target is 4 inches. And then if you look down here with our little servo and our little scale, it's indicating 4 inches. If I come and move it out to 5 inches, it's reading 5. If I move it to 6, it's indicating 6. If I move it out to 7, you can see that it's reading 7. Come into about 2 inches, it's reading 2. Come back to 1 and it's reading 1 inch. This particular sensor will go to about 3/4 of an inch, and so I can't get much closer than that, but you can see it's showing less than an inch there. Go to 2.5 inches, it's showing right at 2.5. 5.5, it's showing right there at 5.5, and we'll put it back here at 4. So you can see this is just a really slick little device that that basically is able to make measurements of distances. This particular sensor will probably go out to about 3 feet or more to make accurate measurements, but so you can see everything here in one field of view. I'm just sort of playing with it on this project from 0 to 6, but when you play with it, you could go out to larger distances if you wanted to. You can see that it's really working very well, and this is really kind of building on a lot of the stuff that we did in lesson number 16 and in lesson number 17. In lesson number 17, I believe it was, that we really went in and learned how to use the ultrasonic sensor. In lesson 17, what we were doing was we were using the ultrasonic sensor to measure the speed of sound. Well, how did we do that? We used the ruler to measure a distance that we knew, 6 inches, and then we measured the ping time, and then we said distance is equal to rate times time. Rate would be the speed of sound, so rate is equal to distance divided by time. We know the distance because we measure it with a ruler. We know the time because that's the ping time that's coming off of the sensor. And so therefore we could calculate the speed of sound. On this one, we're going to do it a little differently. What we're going to do is we're going to say that we know what the speed of sound is, and given that known speed of sound, we're going to come in and we're going to calculate the distance. And so it's sort of like very similar to that other project, project 18, only this time we're calculating distance. The other thing is that we add the servo to it, and we learned how to do the servo, I believe it was in lesson number 16. And so there's not a lot of new programming that we're doing today. We're just kind of combining what we learned in lesson 17 with what we learned in lesson 16 to make this little device. I'm going to go ahead and I'm going to unplug this. Remind me to plug it back in so it's not sitting there jittering around as we are trying to get our code put together. Just a quick reminder of how this little ultrasonic sensor works. Basically, there's an echo pin and there's a control pin or a trigger pin. And when we send a pulse, a low, high, low pulse to the trigger pin, that tells the sensor to send out a ping. And it sends out the ping. The ping travels from the sensor to the target and back. And then it measures how long it takes that ping to travel that distance, okay? So it reports to us a time. The way it reports to us a time is it creates a pulse on the echo pin, and the length of that pulse that it creates on the echo pin in microseconds tells us in microseconds what the time was from the ping leaving and coming back. Always remember that there's a factor of 2 floating around in here. Every time I see students do this, they forget it, that if it's 4 inches to the target, how far does that ping travel? Well, it travels 4 inches to the target and 4 inches back, and so the ping travels 8 inches. So the distance to the target is half the distance that's traveled by the ping, because the ping goes over and comes back, okay? And we measure that pulse width at the echo pin using which command? Do you remember what the command was? It's pulse in. And the pulse in command on the Arduino will show us what how long that pulse is on the echo pin. And so this is all stuff we've learned in the last 2 lessons, but we're going to kind of just do a little real brief recap here. The other thing that you got to kind of look at is the schematic of how I picked it up, hooked it up, and all this is available on lesson number 18 at toptechboy.com, all of these resources. And so this is just sort of a quick recap of how we hook this together. We bring the 5 volts from the Arduino here to this row, and this row we're basically establishing as a VCC rail or as a power supply rail. So anything that we hook to this row will have 5 volts. The top row we're making ground by this connection coming in from the Arduino. Now all of this first row is ground, and so anything we need grounded we can hook to this first row and it'll be grounded. Anything that we need power to, we can hook to the second row and it'll get power. And so on our servo, the red wire is going to the power rail, the black wire is going to the ground rail, and the white wire is the control line, and we have it going to pin 6. So remember when we're setting our pins up that the control line for the servo is on pin 6. On the ultrasonic sensor itself, it looks like we have the echo pin going to pin 11 on the Arduino, and it looks like that we have the trigger pin going to pin 13. So pin 13 is trigger, pin 11 is echo. We've got ground going to ground, and we've got power going to power. And so this is a pretty simple and pretty quick little circuit to get hooked up here. And so what we want then is we want to also then come down here and build some sort of scale so that whatever number we measure, we can come over here and display. And so I made a little one like this. You can kind of follow my lead there and do that, or you can do something better and more interesting. As I grade you in this class, you know, it's great if you sort of follow along and do what I do, but if you want to get to those really top tier grades, you need to be doing something kind of different, sort of like your own idea, and something that's hopefully better than my idea. And it's unusual when we go through one of these projects that some student doesn't come in and kind of do a better job than I've done on it, which is great. That makes me happy when you are doing better things than what I showed you how to do. That's the whole idea. Okay, so you get it set up with the this schematic, and it should look something like this. You can go ahead and start thinking about how you're going to do your scale, but we can go ahead and probably start working on our code at this point and actually start getting this thing coded up. A lot of this should be familiar to you from our earlier lessons. So we always start with a void setup and a void loop. But let's get some of our bookkeeping taken care of up here. What I like to do, first of all, is I like to load any of the libraries that we're going to need. And the ultrasonic sensor does not require a library, but the servo does. And so hopefully you remember how to get your servo library in. Remember, when we're going to include a library, we do it with a pound include. Okay, like that, pound include. And then which library do we need? We put that in these angled brackets. It's servo. That's good. It recognizes it, turns it orange.h. Okay, and remember, you're including a library is one of the few times in Arduino that you don't put a semicolon at the end of the line. Okay, so we're going to load the servo library. Okay, now what I'd like to do is I'd like to go ahead and set up our variables. And what I'm going to do is I'm going to start with our pins. And so let's think, what pins did we need? Well, for the ultrasonic sensor, we had 2. We have a trigger pin and we have an echo pin. So let's set those up. They're going to be integers, and we're going to have a trigger pin, which is going to be what? That was pin 13 we said. Okay, so the sensor trig pin is connected to Arduino pin 13. Okay, what else did we have? We had an echo pin, so we're going to set up echo pin, and that was where we said that that was on 11. And let me just look over there, and yes, it is on 11. Okay, so the sensor echo pin is connected to Arduino pin 11. That's what we said. Yeah. Okay. Now, what other pin did we need? There was a pin that we were using on the servo, and what was that? That was on pin 6. And so what we need to do is we need to say that we've got a variable, declare a variable called, let's call it servo control pin. And where did we have that set to 6? You guys don't have to hook these things up the same place I do. It's just you got to remember that if you're going to do any type of analog write, you need to put it on one that has a squiggly line, on a pin that has a squiggly line. On our trigger pin, we're just creating a pulse, and so that's just a writing a high or a low. We don't need a squiggly line on that. As your projects get more complicated, I like to leave the pins with the squiggly lines only for functions where you really need it, and I like to use the non-squiggly line ones where you don't actually have to have that analog write function. And that way, if you add something, you're always leaving those pins free for a place where you really do need to do an analog write. So this is the servo control pin connected to Arduino pin 6. Okay, so I think that those are the pins that we're going to need, but now we're going to need some variables. Remember, what are we going to measure? We're going to be measuring ping time. That's the time for the ping to go from the sensor to the target and back, so we better have something that will do that. And we're going to be doing a lot of calculations, and so I'm going to go ahead and start making these things floats, real numbers, because we might have a distance of 2.5 or 2 3/4. So we want those in-between numbers. The real numbers in Arduino we declare as floats. So we're going to have a float of ping time, and this is going to be time for ping to travel to target and return. Okay. What else are we going to do? That ping time we're going to use to calculate what? To calculate the target distance. So we're going to have a float target distance. Distance from sensor to target. And we will calculate that from the ping time. Okay. In order to calculate a distance, distance is rate times time. And I know the time, that's going to be the ping time, or I'm going to take the ping time and divide by 2 because of the round trip issue. But I'm going to need ping time, and I'm going to need a speed. Well, the speed is what? The speed is the speed of sound, because that ping is traveling at the speed of sound. So I know what the speed is. I'm just going to put it in the float, and we're going to call that speed of sound. And that's equal to, I happen to know, it's 776.5. And that is in miles per hour. And so this is speed of sound in miles per hour. Okay, and that is when temp is 77 degrees F. Speed of sound depends a little bit on the temperature, so if you want the most accurate results from your device, put in the speed of sound for the temperature that you're at. Okay, so we've got speed of sound in there. Remember, this is miles per hour, because when we get a distance out, we got to keep track of our units, because look at this. I'm putting speed of sound in miles per hour, but my little ruler down here is in inches, and so we're going to have to do a little conversion. And you remember that dimensional analysis. We're going to be having to use that to do some conversions, and just it's not that hard, but we just got to remember. We got to remember to do that. Okay. So what else are we going to do? Well, we get the distance here, but then we're going to have to somehow write a number over here to the servo, and the servo, you sort of write an angle to it, and so we're going to need a variable for that. So we're going to have a float of servo angle, okay, and this is the variable for the angle of the servo. So that's what you'll write to the servo, is that value. Okay. So I think that we have I think we got a good start on getting all the variables that we need for this project. What else do we need to do up here? Well, you remember, for a servo, you have to create a servo object, that you interact with the servo by creating an object. And you can name that servo object whatever you want. You could call it my servo. You could call it my, my whatever. You could call it whatever you wanted, but it needs to be something that sort of conveys what it is. And for me, I'm making a pointer, so I'm going to create an object. What kind of object? I'm going to create a servo object, and it recognizes what that is. Remember, we've loaded the servo library, so I'm going to create a servo object, and my servo is going to be called my pointer, okay, because I'm using it as a pointer. Okay, so this create a servo object called my pointer. Okay, so now we've got this object called a servo that we can work with. I think we're ready for the void setup. The void setup is the stuff that we want to do one time. And what do we want to do? We almost always want to turn on our serial port. So I'm going to go ahead and turn on the serial port. And 9600 seems to be working good these days. So turn on serial port. Okay. What else do we do in void setup? We do our pin modes. How many pins do we have? I think that we have 3 pins that we have to worry about. What's the first one? Pin mode. Okay. Pin mode. Servo control pin. Okay. And that we are writing to it, so that is an output. Okay. We're writing to that, so that's an output. Servo control pin is an output. Okay, now we're going to do pin mode. And what else do we need to set up? Well, we have got the trigger pin. Remember, on the ultrasonic sensor, the trigger pin is also an output. We're going to write to that. Sensor trig pin is an output. Pin mode. What else do we have? We have the echo pin. And we're going to read from the echo pin. Remember that pulse in measurement? We're going to make that pulse in measurement. We're reading from the echo pin. So the echo pin is an input as far as the Arduino is concerned. Sensor echo pin is an input. Okay, the other thing that we got to do, remember, if you're going to do a servo, you kind of got to do 3 things. You've got to make sure that you include the servo library. You have to tell the Arduino where the servo is hooked to. What do we call the servo? We call the servo my pointer, so we got to tell it this servo that we created, my pointer, where is it attached? You want to attach it to which pin? Servo control pin. Okay. So what are we doing? Tell Arduino where the servo is connected. Okay. So servo control pin is 6. So this is telling the Arduino that this servo that we created called my pointer, it is connected to servo control pin. So we named the servo my pointer right here, and we're telling the Arduino attach it to the servo control pin, which is pin 6, which means over here that white line for me has to be hooked to pin 6. Okay. I think we are set up. So We come down here in the void loop, and what do we need to do? Well, we need to make a measurement. We need to make a measurement of this ping time. And how do we make a measurement? Well, we've got to go to our trigger pin, and we have to set it low. We have to create a pulse on our trigger pin, so we start by setting it low, pausing, setting it high, pausing, and setting it low. That creates the trigger that tells the ultrasonic sensor to send out that ping. So we do that how? We do that with a digital write. And we're going to digital write where? Where are we writing? Well, we got to send this word to the trigger pin. Okay, and we got to send it low, so we start with it low. Okay, so we're going to set the trigger pin low. Now digital write. What do we want? Oh, what we want to do is we want to delay just a little bit there. We want to pause to give that signal a time to settle. So we're going to say delay in microseconds. About 2,000 microseconds. You can play around with these values, but 2,000 microseconds is 2 milliseconds, which is 2/1000th of a second. And so pause to let signal settle. All right. Now what do? We're going to digital write trig pin, and this time we're going to put it high. Okay, so we're trying to create this pulse. We started low, we go high. We're going to make a pulse. Okay, set trigger pin high. And now what do? We delay a little bit so that, and we'll go ahead and do a delay microseconds. You don't have to delay very long. Let's make it 15 microseconds, say. Okay. Pause in high state. You just want to stay there a little while to make sure that the sensor sees that you sent it the trigger. Okay, and now to make sure that it is a pulse, we got to bring it back down. And so now we're going to digital write, and we're going to write to the trig pin, and then we're going to write it low. Bring trig pin back low. So you can see what we just did is we created a trigger. We created a trigger on the trigger pin. So we started low, waited, went high, waited, and came back down. Okay, so we created that pulse. That pulse tells that sensor, send out your ping. And since it's sending out the ping now, we need to go measure that ping. And what variable are we going to put that number in? Well, we said it was going to be ping time. How do we do the measurement? We do it with the pulse in command. And we got to tell pulse in where we're going to read it. Where do we read it? We read it from the echo pin because that's where it's sending it to. And then we read it. We're looking for a high pulse. This is just saying, this is telling the Arduino that the sensor will be sending it a high pulse. That's something that goes low, high, low. That's a high pulse. A low pulse starts high, goes low, and comes back. But we're looking for a high pulse, okay, with this measurement. So this is measure ping time at echo pin. That's pretty straightforward, I think. Okay, so now we have this ping time, and this is in microseconds because that's what microseconds is what this this sensor outputs. Okay, so now we've measured the ping time in microseconds, but microseconds is not a very useful measure because we did not put we got to get these units to match, and so our speed of sound was in miles per hour, and so we better not be dealing in microseconds. We better get ping time in the same units, and for the case of time this would be hours. So let's do it in steps. So ping time is going to be equal to ping time. First of all, let's get it into seconds. Well, to convert microseconds to seconds, we would divide by 1,000,000 because there are 1,000,000 microseconds in a second. And so this is, again, dimensional analysis. And so I think one day I need to do a whole video on that, but divide by 1,000,000, so that's 1, 2, 3, 4, 5, 6. All right. So this converts ping time to seconds. All right, but we were not dealing in seconds. We are dealing up here in miles per hour on the speed of sound. So we better get this in hours. So ping time is equal to ping time divided by how many seconds in an hour. Well, there's 60 seconds in a minute and 60 minutes in an hour, so we would divide by 3,600. Okay. And it's just really, really good practice to do your division with floating point numbers. And so if you come in and look at this, I put a decimal there that sort of makes sure that I'm always forcing these things to be floating point math, so I don't get some strange integer operation going. It just, a lot of times when I see mistakes or I see perplexing problems helping students debug, a lot of times it's like some integer math has crept in on us, and just a good practice to keep that from happening is to put decimals at the end of our numbers, and that kind of forces it to be floating point math. Okay. Converts ping time to hours. All right, so we're in hours there, so that's pretty good. That is pretty good. Okay, so now we should be able to calculate the distance. So target distance, let's make sure that's the variable we set up here. Target distance is going to be equal to what? Distance is equal to rate times time. Well, what is rate? Rate is the speed of sound. And we entered that up here, so this is going to be speed of sound. Okay, distance is rate times time. The rate is how fast the ping is going. How fast is the ping going? It's going the speed of sound, and we entered that up there. Distance is rate times time. Well, what's the time? The time is the ping time. So we can put this in, ping time. Okay, so what does this do? This calculates distance in miles because the speed of sound was in miles per hour. So we'll take care of that. The other thing we got to remember is that this distance is the distance traveled by the ping, and the ping comes from the sensor, goes to the target, and comes back. And so if I'm 4 inches away from the target, that ping travels 8 inches. So if I want actually the distance to the target, I need to divide by 2. So target distance is equal to target distance divided by 2. Okay, and what does this do? This sort of, how can we say this? This accounts for round trip of ping to target. Okay. So now we're not reporting how far the ping traveled, we're reporting how far it is to the target. So that hopefully that makes sense. All right, so now the problem is target distance is in miles, so target distance would be equal to target distance, and then what we're going to do is divide by the number of, or multiply by the number of inches in a mile. So that's 63,360, okay? And that is convert target distance to inches, because there are 63,360 inches in a mile. All right. Always got to keep track of our units. Usually, most of the mistakes that I've seen engineers make in their life, and sometimes they're catastrophic mistakes on projects, is not keeping all the units straight. So we want to be very good about keeping track of our units. But up here, we converted the time from microseconds to hours, and then here we're converting from inches to miles. And so I think that we should be in pretty good shape on our things at this point. All right, so what I'd like to do is I'd like to just sort of check this out at this point before I try to go in and get the servo. Let's just see if we have our math working right. And so let's go ahead and give it, let's go ahead and play with it a little bit. And so what I'm going to do is I'm going to say serial dot print, and then I'm going to say in quotes the distance to the target is, close that quote, close it, Okay, and remember that whatever you put in the quotes, it just prints that out exactly. Okay, and then I'm going to do serial.print ln, and then I'm going to put, what is our variable? Target distance. Okay, close that, and then serial.print. And I don't want this. I'm going to put my unit. So this is just going to be a print, so that doesn't advance the line. And so now I have serial print line. And then what I'm going to put here is the units, which is inches, because that's what we converted it to. Okay, and now I'm going to put a delay in here just so that it doesn't go too fast. Delay of 1,000 milliseconds would just make it give me a reading every second. So let's see how many mistakes I've made here. I've tried to be careful. Oh my goodness, what did I do here? Digital write. Ooh, okay. Now this is something interesting to just sort of help, and this should have been trig pin. That doesn't matter on a comment, but just to be careful. Now you see, look, when I do this, it gives me an error on here. Man, everything looks right here, but it says expected a token, this semicolon before digital write. So the error isn't here, the error is here. So sometimes it's before or after where you actually have the problem. Okay, it looks like it's happy now. One mistake on all that is not too shabby. So let's take a look here and see what happened. Look at that. Distance is 4 inches, just like we got it set there. Very, very good. If I come into about 2 inches, I'm reading pretty darn close to 2. Let me adjust that a little bit. I'm reading just right at 2. If I come out to 3 inches, I'm reading right at 3. Okay, if I come out to 6 inches, I'm reading right at 6. And so I am making most excellent measurements, most excellent measurements. That side of the circuit is working. Now we got to come over here and we've got to get our little distance meter working. And guys, this is like one of the most important things that you're going to learn in these lessons. And that is, you know, this is what I see when I'm teaching this class to high school students. They'll come in and they'll just draw a scale, and then they'll start like playing with the numbers, playing the numbers that they're writing, trying to get things to match, and just trial and error, trial and error, trial and error, trying to get it to 0.1 when they have it at 1, and trying to get it to 0.6 when they have it at 6, and ended up with a whole bunch of if statements and all this different stuff, trying to get this to point where they want it to. That's not how you do it. In engineering, you don't want to do things by trial and error. In engineering, you want to use the math that you know. Okay, and this is the thing I see, because I teach math for half the day and I teach engineering for half the day, and a lot of times it's the same students that I have in both math and engineering. And this is what happens. The kids come in my math class and they know how to do a line and they know how to do their math, and they have y is equal to mx plus b, and they get 100 on the homework and they get 100 on the test, and they're in the 96th percentile on the ACT. But then they come into my engineering class and it's like they never worked a math problem in their life. They just start guessing, just start guessing in trial and error. What we have to do a better job as teachers, and what you have to do a better job as a student, is taking that math that you're learning in math class and taking it out of math class and applying it in other classes. It's like you come into my math class and I give you this little toolbox that has all these neat little tools in it, all these very powerful, very valuable little tools. And you got this little toolbox and you know how to use every tool. But when you leave math class, you leave the toolbox in my room. And when you come in engineering class, it's like you never saw any of this stuff before. Take those tools and take them to your other classes, okay? That's what we got to do better at. So how are we going to do this? Okay, how are we going to do this? Let's go back. Let's go back and look at some of the math. Okay, the first thing you got to decide is what you want to do. So what I did was I got a piece of graph paper, because the servo is in angles and it sort of is roughly from 0 to 180 degrees. And so the easiest units to work with are in angles. And so I got this polar graph paper, which is sort of like a protractor. You can print your own out. I give you a link here on lesson number 18 at toptechboy.com. But basically you can get that at printfreegraphpaper.com. And I'll try to show you the link here. If you come over here, I think I have it in here. You can get your graph paper right here. And you see you can just go there to their website and then you can print that, and it's really slick graph paper. Okay, so you get that graph paper and then that gives you something to kind of work with. And then what I knew was I knew that I sort of want to go from 0 to 7, and I know that the servo cannot go from 0 to 180. And so I wanted something that kind of looked good, and I wanted something that would sort of also kind of match up with these grid lines on the graph paper. On the graph paper, these major grid lines are 15 degrees each. And so like if I start over here at 0, let's see, 15, 30, 45, 60, 75, 90. So you see each one of those is 15 degrees. And then I kind of wanted to not come all the way over here because I knew my servo wouldn't come here. So this would be 30 degrees here, or this would be 150 degrees here, and this would be 30 degrees here. But then also what I wanted was I wanted the 0 or the 7 to kind of be in the middle of that range. And so this would be about, or let's start over here, this would be about 30, and this would be 45, and kind of halfway between 30 and 45 is right here would be about 37. And similarly here, you're kind of between, let's see, this is 180 minus 30 would be 150, between 150 and 150 minus 15, you would sort of say 150 minus 7 would be right about here, which would be about 143. So on mine, what I want to do is I want the range of the servo on the meter to go from 37 degrees to 143 degrees, and that way it goes in a nice smooth arc over this range. Hopefully that makes sense what I just said. Then with that, what ranges do I want to measure in? Well, my thing here goes to 6 inches, but I could cheat a little bit and go out to 7 inches. And so I want to measure a range from 0 to 7 inches. Okay, so I want to measure a range from 0 to 7 inches, and I want that to make the servo go from 37 to 143. And if I do that at 0, it's going to be 37 and point here. And then at 7, it's going to be 143 and point at the 7, and then it'll point at the right number everywhere in between there. And believe me, I'm explaining this in excruciating detail, but if you'll just go through the 3 minutes to do the math, it's way quicker than sitting and spending 3 days in the trial and error in the way that I see people do it. So what do? What do we want to end up with? We want to end up with a servo angle. Servo angle depends on distance. Okay, distance is your independent variable. The distance that you measure, the distance from here to here, is your independent variable. That's what you measure, and based on that you calculate the servo angle, which is your dependent variable. This is your independent variable, and I might have misspoke a while ago. This is your independent variable, the distance, and your dependent variable is the servo angle. Okay, so on this scale I go kind of 0 to 8 on my graph on distance measured in inches. That's from over here, and then I want that to go from I make the scale from 0 to 150 here so I can graph it. Well, what are my 2 points? I know that when I have a distance of 0, I want it to point at 0, which would be 37 degrees. So my first point is 0, 37. That's 1 point. That's the point right there. When I'm at 7 inches, okay, that's out here, it's 7 inches, I want it to point at 7, and that would be 143 degrees. So my second point is 7, 143. I have 2 points. I can define a what? I can define a line. The slope is y2 minus y1 over x2 minus x1, which is going to be equal to 143 minus 37 over 7 minus 0, which is equal to 106 over 7. The slope is 106 over 7. What do we know the point-slope equation of a line is? y minus y1 is m onto x minus x1. You can pick this as your point or this as your point. Because this has a 0, this one would be easier. I'm going to use this. Either one will give you the same answer. I like to pick the easy one. So y minus y1, what is y1? 37. Y minus 37 is equal to m. What is m? We did that up here, 106 over 7 times x minus x1. x1 is 0 because it's right there. So y, take that 37, move it to the other side. So we have y is equal to 106 over 7 times x plus 37. Now let's rewrite it in the variable names that we're using. This is x and this is y. So what is our x? That is distance. And what is our y? It's servo angle. So this is really cool. Servo angle, where we write the servo is going to be equal to 106 divided by 7 times distance that you measure there, plus 37. And boom, you're going to get it to work perfectly the first time, and you're not going to have to keep doing all this nonsense trial and error stuff. So let's remember this equation. Let's see if I can come back up here. Okay, so I'll try to see if I can get this where I can see the equation. Okay, so what are we going to do here? We want to calculate the servo angle, right? We want to calculate the servo angle. So, the lowercase servo angle is going to be equal to what? 106. Remember to always put that decimal sign there so you don't get any goofy integer math going on, divided by 7 point times, that's the slope, times what? Target distance, because that's the variable that we used, right? The variable we're using is target distance. Okay, plus 37. Okay. Now, that is the angle that you want to put the servo at. How do you put that angle on the servo? Do you remember that? You do a right. What do you write to? Whatever you named your servo. I named mine my pointer dot right. I'm going to write that number, servo angle. Okay, and I need to put some comments in here, and ooh, no semicolon, pop that. Okay, so this is calculate servo angle based on target distance. And here what we're doing is write servo angle to the servo my pointer. And then we always need to put a little delay in here. I'm going to delay a 1/10 of a second. Delay to slow things down. All right. Let's see if this is going to work. Looks like things are happy. Things are going. Remember, got to plug this pin back into pin 6. I unplugged it so it wouldn't be moving around. Okay. Look at that. Okay. Looks like it's pointing right at 6. If I bring it to 3, it comes back to 3. Okay. If I put it out here at 7, it's coming to 7. I slowed this thing down too much. Remember this delay? We need to get rid of that because that's going too slow. That's great for printing, but it's a little sluggish when I'm sitting there playing with the distance. So let's re-download it. Okay. So now let's come back to 6. Yeah, now it's nice and sensitive. Look at that. Look at this, guys. 4, right on the money. 1, right on the money. 2, right on the money. 3, looks good. 4, 5, 6, 7. Wow, look at that. Look at that. Works perfectly the first time. Why does it work perfectly? And that's at 2.5, and look at that, right there between 2 and 3 at 2.5. Why does it work perfectly? Because we did the math. We did the math. Guys, you know how to do a line. And just think, What is it that I'm measuring? I'm measuring distance. What is it that I want to map that to servo angle? So I have servo angle depends on distance, okay? Do the math and look at it. Man, you can work this problem 3-4 minutes, and then the thing works perfectly the first time, and you don't have to go in and do all this all this silly guessing and this silly trial and error. Well, I think this has been a really cool project, and I think it's pretty neat that we can come in and that we can measure distance and then we can convey it to the user in a in a you know, kind of in a slick and neat demonstration. Now, what your assignment is that first of all, go in and do this, sort of follow along with me and do what I've done here. But then I want you to come up with a better way to do the display, and you can use other components in your Sparkfun kit, or you could maybe, you know, maybe you would want to build something on the 3D printer. You know, fire up AutoCAD and then print something out on the 3D printer where you had a really elegant scale with the with the servo. Or use, you know, maybe you want to break out and use the LCD display. But do something. The requirement is that it's got to be something moving past just what we've done here, something better where you're putting your own ideas into it. And requirement number 2, somewhere in there you have to show me that you're calculating something based on something else. I mean, you've got to show me that you're going in and doing this mapping function. You're starting to apply that math that you know to the engineering projects that you're working on. And so that's your assignment. I'll give you several days to work on this, to first of all do what I've shown here and then take it to that next level. Okay. Again, this is Paul McWhorter from TopTechBoy.com, and hope you will tune in shortly for Arduino lesson number 19. Talk to you guys later.